Hello, my name is Grant Anderson. I'm the President and CEO of Paragon Space Development Corporation. But more importantly, I'm here moderating a panel today on the environmental control systems. And what our question is what are the long poles in the tent to get ECLSS ready for the trip to Mars and on to Mars? And what will Artemis show us during that time? I've got a great panel of people that are deep into the game here, all the way from the customer, NASA, down to the technologists that make things happen. And so we're going to dive right into this. First of all, going to the next slide. One more slide, please. Thank you. Yeah. Well, our four panelists today are Robyn Gatens, who's the Acting Director of the International Space Station and ECLSS CHP Systems Capability Leader. Ted Bonk from Honeywell, who's a Technical Fellow and in the Space Exploration Application Engineer. Darren Simplasket from Collins Aerospace, who's an Associate Director in Business Development there. And Chip Link from Dynetics, who's the Crew Module IPT Lead for the Human Lander Systems in the Space Systems Division of Dynetics. Next thing, really what we're trying to ask here is what are the long poles in the tent to get ECLSS ready for the trip to Mars and on to Mars? How will Artemis help us do that? This is the Humans to Mars conference, but of course, looming in front of us is the boots on ground requirements for the moon program. And so we're going to be proving out a lot of things on the moon that we're eventually going to take to Mars. So we're going to talk about that today. And then on to the next slide, just a little bit of an orientation here. This first 3 minutes, I'm just giving you the panel on purpose, which I just did. We're going to get a presentation by each panelist a little bit, Robyn and then Chip and then Darren and Ted. And then we're going to go on to questions that I will ask the panelists for about 40 minutes, and then we'll open it to the audience participation. So please use your capabilities to put in questions if you have them, and we'll do a little bit of 2-minute wrap up. This whole thing is about 1 hour and 30 minutes long, so we expect to be done at 30 minutes after the hour. That's 3:30 Eastern time. So without any further ado, I'd like to introduce Robyn Gatens, and Robyn, take it away.
All right. Good afternoon, everyone. Thanks for tuning in to our panel this afternoon, and thank you for the intro, Grant. This is year 3 or 4 for me to participate in a panel like this for this conference, and I've always enjoyed the collaboration with the team and talking to this audience. So given the theme that we're looking for today, as far as what are the long poles for Mars and specifically ECLSS, I put together a perspective from NASA and some work that we've been doing over the past year or more, and really looking at lessons that we have learned so far on the space station. What has that taught us about our ECLSS system readiness, and how do we get from where we are today on space station to that system being ready to support missions to Mars. Next slide, please. The next one, yeah, there you go. So when we think about missions to Mars being anywhere from 700 to 1,200 days, the kinds of missions we're looking at, this is an order of magnitude different problem than we've experienced in any of our previous human spaceflight missions. There on this slide, you can see at the bottom the different human spaceflight missions over time. And the dots represent the amount of time that mission has gone between launch and landing or a resupply mission. So if you take all the missions leading up to space station, which is our current experience, space station, we haven't gone much more than 100 days without the ability to resupply and bring spare parts and consumables. So we compare that to a mission to Mars, you can see how much of a more difficult problem than we have to support a mission to Mars. So there's our challenge. Next slide. And then when you take that a little bit further, you need a successful mission, right? So somewhere along the way, we're going to define a probability of a successful mission target for a mission to Mars. The term we use for that is probability of sufficiency. And what we mean by sufficiency is, are you going to have enough consumables and spare parts to have a successful mission? And so if you define a probability of sufficiency somewhere up in the 0.9 something range, then that defines your spares mass that you're going to have to take with you to support your system. And this slide just illustrates that these two are interrelated. You define your maximum spares you're allowed to take, well, that's going to define your probability of sufficiency. You define your probability of sufficiency, that's going to tell you your maximum, the amount of spares that you're going to need. The point I wanted to make here is testing is a first order driver that really helps us drive down the amount of spares mass that's going to take to achieve that probability of sufficiency. And I'll talk a little bit more about that in an upcoming slide. Next slide, please. There are a lot of components that make up the mass for a mission to Mars, and mass has always been a big driver, and it's going to be a driver again. You probably heard earlier panels talking about mass for a Mars mission. So we look at a round-trip mission to Mars, and what that habitat mass is going to be somewhere in the 45 to 50 ton range. It's made up of systems, it's made up of spares to support those systems, and then it's made up of different consumables at the top, those kind of three main categories. You can see the items outlined in the dashed orange are the ones related to Eclipse and crew systems. So a significant portion of the vehicle mass is made up either by the system itself or the spares associated with those systems and the consumables. A couple of the big drivers to point out, food. So food is a large mass driver. Obviously, we have to carry food for the crew, but most of the mass of food is water. So we're looking at how are all these things interrelated. The more we can recycle the water, the less water that we need to be bringing in our food. So a lower system mass solution is a combination of less water in the food, but more recycling with our Eclipse system. Similarly, if we carry more loop closure, that's going to add to our initial system mass, but then it's going to reduce our consumables. It could increase our spares, though. If we bring more equipment to recycle the air and the water, then we're going to need more spares to support that. So all these things are interrelated, and it's our job to do that system analysis and try to optimize between all of these drivers. Next slide. So the experience that we've had on space station has been invaluable in order to reduce the amount of spares that are going to be required for future missions. This slide shows that when we flew the regenerative Eclipse system to the space station back in 2009, pick a line. So for a probability of a sufficiency, if we had tried to go to Mars back then, and say we wanted to achieve a probability of sufficiency for that mission of 0.99, or the blue line, given what we knew about that system and the failure rates associated with it, the predicted failure rates, we would have estimated we would have had to take about 8 tons of spares to support that system on a trip to Mars. And we probably would have gotten it wrong. We probably would have packed too much of one thing and not enough of another. Fast forward to today, we've refined what we know about that system. We have reduced that uncertainty, and we've brought that amount of predicted spares to support a Mars mission from somewhere in 8 tons down to somewhere just below 6 tons. We've had a 30% reduction in projected spares to support that mission just over the last 10 years of testing on station. But that's a long period of time. It takes a while, and we need time on system to achieve that level, that reduction in risk and uncertainty. So if you project that out, if we keep testing on station, which we intend to do, then we can further bring that down another couple of tons, and that will help us achieve that mass target for Mars. Next slide. So what are we doing? We've got a lot of upcoming ECLSS upgrades to our current ECLSS system, as well as new capabilities we're flying on station, and then we're going to test the heck out of them. There's shown in these pictures are some of the things we're already doing. We're not flying a brand new ECLSS. It's a combination of some new technologies, some upgrades to existing technologies, and improvements to what we have. So we've got, for example, the thermal amine scrubber that Darren's company provided. That's already on board station, one of our CO2 removal technology demonstrations. We're planning to fly our universal waste management system, or our toilet. And there's the toilet stall, getting ready for it. On station already. We've got a microbial monitor. It's a new capability that we can use to monitor on board what we have in the air, water, and surfaces. Upgrades to our urine processor. There's a new distillation assembly that's up there now, waiting to be installed very soon. We've been doing testing with our Cygnus vehicles on Sapphire, which is large fire demonstration tests, and we've just completed our 4th one, getting ready to fly the 5th one. We've got another atmosphere monitor, environmental monitoring piece of equipment, the spacecraft atmosphere monitor on board station, and an enhanced version of that flying next year. And then some logistics trackers we call Realm. Next slide. And I mentioned the new toilet going up. We're very excited about this one. It's launching on NG-14, and which is the next cargo mission out of Wallops at the end of September. So we're looking forward to getting that on board. This is a copy of the toilet that is also going to be flying on the Orion spacecraft. So we're going to be testing it on both the space station and Orion for use on all of our future vehicles. We've got a brine processor assembly from Grant's company Paragon flying up next year, and this is going to close our water recovery gap. Right now we're sitting at just over 90% of recycling our water on space station with the water and urine processor we have, but we throw away the brine. So this assembly is going to take that brine and recover that water that we're currently throwing away and get us over to over 98% total water recovery. And then we've got another CO2 technology flying that we call the 4-bed scrubber, and that'll be flying next year as well. And the Airborne Particulate monitor is going to measure particulates for the first time on space station. This is a new capability and will be important as we start to do missions where we encounter dust from surfaces that are respiratory hazards to the crew. And this Airborne Particulate monitor is also flying on the next Northrop Grumman cargo mission. So this is just a few highlights. We've got a lot going on, and we're very excited about continuing to upgrade the ECLSS that we have on station. Next slide. This is my last one, get off the stage. So just to summarize, the ECLSS and crew health and performance systems are a big driver for Mars mission mass. Over on the right, you see kind of where we are today on the International Space Station. We've got 50% water in the food. We're recovering a little less than half of oxygen from CO2, and that 90% water recovery. And where we think we need to be for Mars is we're trying to reduce the food water content, like I mentioned, recover more oxygen from CO2, and get that water recovery up to over 98%. But that box at the bottom is what we're really focused on too, is today on station we enjoy being able to frequently supply spares and do maintenance with routine cargo flights from Earth. We're not going to have that from Mars, so we need to reduce the spares through both improved reliability and maintainability. So our test experience has already helped us along that path. But we need further investments in this area. So we're focusing our investments in targeted upgrades to the system and additional long duration testing, which is so critical. We'll get that on station. We'll also get that at the gateway And then as we deploy systems to the lunar surface, we'll get additional experience there that'll all be helpful as we prepare for the Mars mission. So with that, I'm done with my opening comments.
Okay, thank you very much, Robyn. Yeah, I know that as far as the reliability and maintenance, it's not only reducing the number of spares, but the size of the spares when you need them too. Okay, so I'd like to hand it over to Chip now. Chip Link from Dynetics.
Thank you, Grant. And I appreciate being here. Good afternoon, everybody. I'm going to spend a few minutes, if we can get the charts up, and talk about the Human Lander Program. Robyn, that was just an excellent lead into discussions on the Lander Program and the challenges with mass and spares and, becoming more Earth independent. So, all of those are a big reality in the Lander Program. So if you go to the next chart, next chart, there you go. So this chart is something maybe some of you have seen. It's kind of the roadmap or the trajectory of the Artemis lunar program, and kind of groups in, the Gateway, Orion, and the lander, and then the additional capabilities that I think we'll see being on-ramped in the next several years. So starting from the very left there, you can see the program right now is focused on human landing systems and putting those in place and demonstrating those so that we can get a solid capability to get a crew down to the surface of the moon and back safely to the Gateway and back safely to Earth. So, that's the initial objective. So once we go beyond that, then, we're going to leverage the Gateway and the Gateway logistics program to enable us to get more mass up to Gateway and then down on the surface. Mass is really a big constraint on landers, and initially that's why you're going to see most of the up mass being taken for the lander just to perform the initial demonstrations. And then as we gradually get more refueling capability on board and on orbit, as well as logistics and being able to stage those and get those down to the surface, you'll be able to see a lot more functionality and capability on the surface. And that's kind of what this chart illustrates, is as you move to the right, as we move forward, you see those capabilities incrementally increased. Next chart. So we have, I think most everyone's aware, we have three providers that are working on the HLS program, and they're all unique in their own way. The national team approach is a little more traditional, similar to what we've seen in the Apollo program previously. It's a two-stage system with an ascent module that's separate. And then the two providers on the left are reusable vehicles of some degree. And of course, SpaceX has a tremendous capacity to get more mass down on the surface and back up. And then the Dynettix Design, which is what I'm working on at this point, is focused more on cargo delivery and surface access, as well as crewed capabilities as well. So if you go to the next chart, I'll talk a little bit more about the Dynettix Design. It's innovative in that it's a single stage vehicle. There's no separate ascent module. The whole vehicle lands and then returns to Orion or Gateway. It's sized for a 4-person crew really for extended missions. The initial mission will likely only be for a lunar orbit, which is about 7 days. But it's really sized and capable of longer duration missions with up to 4 crew. So that's our design point. And of course, it's fully reusable. It's designed to be restocked and refueled on orbit from the Gateway. And I think the discriminator on the Dynettix design is its capability to deliver payloads and other capabilities to the surface. So you can see in the image that the center module is a pressurized crew cabin, but that could be other payloads as well. So we're working on capabilities that will allow us to fly and deliver larger payloads directly to the surface. We can move payloads. We can collect payloads at the gateway and fly them to the surface. So it's really a very extensible type design for missions that we see in the future for lunar support. Okay, and just my last talking chart next. I think Robyn had a great lead in on this. Really, the lunar landing program is really the next step to get these technologies up, get capabilities in place, not only with just a lander, but with surface halves and other things that are going to have more capabilities and more capacity to do, the type of work that needs to be done to prove some of these technologies. Initially we're going to have, just essential crew functions, but, we see that growing significantly to something that's more close to what we're doing on ISS in terms of research and development of these systems. So, I think that's where we're headed, and it's going to be a huge enabler to get these systems running, so we can have some safe missions to Mars. And Grant, back to you.
Okay, well, thank you very much, Chip. Our next presenter is Ted Bonk from Honeywell. So, Ted, take it away.
Thanks, Grant. Thanks, Grant, for hosting this panel. You always ask questions in unique ways to make us think a little bit more. And so, like the challenge, okay? So, I'm from Honeywell, and we started looking at what the long poles to getting to Mars would be, and it talks about basically it's proving and demonstrating the reliability of life support. If we go to the next slide, one of the things we will typically do is when we want to achieve something is pick a point in the future of success and then figure out what's going to take to get there. And so we looked at a Mars mission scenario, and these are rough numbers, where you take about a year to assemble a Mars transfer vehicle in orbit, and then about a year to get there, a couple years on orbit, and then a year back, and then if the equipment is built in normal space fashion, it's about another year. So successes would be a point of completing the 2-year mission on the surface with operational life support in the Mars transfer vehicle and the ascent vehicle and the surface systems, and getting ready to leave orbit. This means about a minimum of about 6 years of continuous life support, about between 3 and 4 different vehicle types is needed. And so that's a significantly long time. So if we go to the next slide, when we look at other systems outside of space, where groups and companies and industries have looked at how to increase reliability, there's some lessons learned. There's lessons learned from space. And so, one of the ones I've encountered early in my career was a twin-engine large jet airplanes. They went from 4 engines to 2 engines. And so how did they do that? And they went through some an enhancement test program to make sure that even if one of the engines failed, that you can still make it across the Atlantic or the Pacific. You have another area of technology with fly-by-wire control systems that automatically change and reconfigure things on failures. And then I don't believe I started thinking about this, and automobiles used to be a whole lot less reliable. But now you buy one, you expect it to last over 100,000 miles without any major significant trouble. How are we doing that? There's characteristics that we can learn from that. There's many smart people working on this and space problems that we can look at increasing, lessons learned on on Mars type systems, redundancy with independence, surge performance in case of emergencies or contingencies, switch over to redundancy units or dissimilarity for common mode faults. Can you get quantity in to improve reliability through a continuous improvement program? And at the same time having robust subsystems such as thermal and power in order to support the life support systems. These are all things that go into making a reliable system and have impact on the equipment design. So next slide, please. We go to the next slide.
We're seeing the next slide here, Ted, so if you're not.
Okay, now I've got it. So ultimately, the technology we have today, we're going to need to make it a little smarter with more communications capability. So we know how it's working on duration, extended duration flights, how it's working when there's no crew, which means more communications, more sensors for insight and diagnosis. Probably in some places there'll be some internal redundancy of select components. Additive build and replacement for some spares is definitely something that will be built into these systems for reduction of total mass going to Mars. We'll see onboard prediction for monitoring, diagnosis, and helping to repair the systems, and likely some type of adaptive performance capability for emergency situations where you can run a particular piece of equipment to something that's slightly outside the nominal in order to deal with that type of situation. When we're trying to build these, we think we're going to see a more movement to more commercial type parts that have widespread use as piece parts of some of the life support. We also think that there's some benefit to looking at building all the units for a selected mission and then selecting the ones that are provide the best performance for that mission, and then build of all the end items closely in time minimizes any variations that might be introduced in the manufacturing process. And then learning from all the data that's being gathered from an ISS or the gateway or other instantiations to work as a feedback through a reliability enhancement program feeding forward into the equipment for the next mission. Next slide. Well, we think the long pole is demonstrating that we have a reliable system or set of systems for life support. And some things we think that might be worthwhile doing is moving through at the component level, test, analyze, and fix, basically pushing those components to the point where you can clearly establish the limits of what they can do while you're collecting that data. Life testing on particular components to see how long they will actually last. Basically taking something and let it run and collecting all the data on that, performing some teardowns if necessary. And then pilot plants of integrated Mars life support equipment, whether on the ground or using the gateway as an analogy, you run and collect that performance data. And as you're collecting all this from all these equipment installations, you can use failure analysis and replication of that data to feed into the equipment design or operational changes that may be needed. Minor updates, tweaks to that basic concept to keep the things working as optimal as possible. And then use predictive models to predict what things might fail and failure analysis on the ground and for onboard use to help the crew. And then anything you learn through this, incorporate that into the equipment for the next mission in order for you to have a higher chance of success. And eventually, the need for this becomes less. But right now, the amount of test time that we actually have on life support systems outside of low Earth orbit is really limited. And that's all I've got.
Okay, Ted, thank you very much. And last but not least, our fourth panelist today is Darren Simplasket from Collins. So take it away, Darren.
Thank you, Grant. Pull my slides up. So thanks for inviting me to this panel. This is actually the second time I've been on this panel, so good to be back. Like Grant said, I'm Darren Sampleski from Collins Aerospace. I've been with Collins for the past 24 years, working on a variety of life support systems. I've had the pleasure of working on the development of multiple systems, including the oxygen generator, the water processor assembly, and was actually the chief engineer on the Sabatier assembly. I also was the program manager for several of our next step programs, looking mostly at modular Eclipse for the gateway. So we've learned a lot about that and can apply a lot of those lessons back to this. My current role is the Director of Business Development for our Crewed Vehicle Solutions Group. If we want to move to the next slide. So I went at this looking at, what do we need to do to create reliable systems for Eclipse? We're going to have a lot of challenges going to Mars, stopping at the moon first. So what I did is I took a look at the current state-of-the-art system. What do we have today? So when you look at these systems, they were highly engineered systems that were assembled and tested in a strictly controlled environment with lots of oversight. So kind of built like they were a Swiss watch. So very, very controlled. These systems that we had on the International Space Station, they were also designed as ORUs, so orbital replacement units, where things like repair weren't really considered, right? So if something broke on orbit, you simply pulled out the module, you brought it down. Some of these orbital replacement units, weigh several hundreds of pounds. So when we had the space shuttle, we had a way to get cargo back and forth quickly and easily. So it wasn't really an issue. And so, the reason they did that is because they didn't want the astronauts, focused on repairing items. Their reason for being on the International Space Station was, to do experiments. So, we only did maintenance, or we only do maintenance as an exception. Although, since we no longer have the shuttle, we do more maintenance than we originally did on the International Space Station. Another big aspect is, all of this equipment is monitored by a team of specialists on the ground. So, every day there's a whole group of people looking at this hardware, looking at data coming down and analyzing it. When we do a mission to the moon, and especially when we do a mission to Mars, you're not going to be able to do that, right? There's a large communications delay. So you're not going to be able to simply look at the data and make changes. Another thing, that we had done on the original hardware was there was no real plan for common hardware. So even though, a lot of companies may have used the same hardware, there was no plan across the board for all of this hardware. So for instance, NASA had selected quick disconnects, for use on a lot of this equipment, and companies like us and Honeywell and Paragon had all gone off and used those same quick disconnects, but every one of the companies had used a different part number. So there's no way to cross-reference. So I think, going forward, that's one of the things we need to do. And then finally, the control architecture, right? So this control architecture was developed probably in the 80s, maybe even in the 70s, and then implemented in the 90s. And that's kind of been what we've been controlling the space station hardware with for the past 20 years. I think my iPhone probably has more capability than the systems we currently use on orbit. You want to jump to the next slide? So where are we going? How do we get to Mars? It's just taking a look at the two pictures on the left. So those were the modular Eclipse systems that we had developed for the Next Step program, specifically looking at repairability, so that the units on the bottom are actually repair demonstration units. What we learned from all this is, we really need to put together some sort of robust plan for testing these systems, both on the ground and then in orbit before we ever, attempt to go to a mission to Mars, right? Probably several years. We've learned a lot on the International Space Station over the 20 years, and hardware doesn't react like it does on the ground, but you need to do that ground testing first, and then eventually do that same level of testing in orbit. Another thing that we really think we need to do is to specify the use of common parts and common interfaces, right? So if I develop a system, and there's an issue, somebody else can potentially have those same parts on orbit. Really reduces the amount of spares that we're going to have to take up. I think as Ted talked about, control architecture, you really want to incorporate intelligent systems. I'd like to see systems that, when they're in use, if there's a potential problem, the system can self-diagnose itself before it becomes a catastrophic issue. Currently on station, we often go back and look at the data after a system has failed. And had we been, monitoring that data all along, we may have been able to avoid the catastrophic failure, at least, slowed the system down or done something to prevent it from completely failing. Another thing that, we really need to do in the future is look at hardware designs that are specifically designed for in-orbit repair. So like I said, on our next step programs, we had looked at what we call maintenance units. So much smaller subsystems as opposed to the ORUs. So, instead of replacing a 300-pound ORU, maybe you're replacing a 5-pound maintenance repair unit. Another thing that we always look at is astronauts. They're not specifically trained as hardware technicians. A lot of our astronauts today are highly specialized in whatever their field of study is, and a lot of PhDs. We really should probably consider sending up that auto mechanic that can repair almost anything. You're going to need someone like that on a mission to Mars. Not to say that some astronauts aren't capable of that, but the majority of them probably are not trained to do that. Like I said before, we really want to limit that reliance on ground support. A mission to Mars, you're not going to have that. We should probably try that out on the moon first. You could probably have some limited ground support for missions to the moon, but you really want to test that system out before we make that mission to Mars. Another thing that we looked at was the use of augmented reality and virtual reality for maintenance. So under our next step programs, we had focused in on could we do something with augmented reality? What we learned is that you could put together programs so that you could do repairs where the technician could put on that set of halo glasses, see the hardware, and the system would walk them through how to fix something real time without any ground support. And then finally, let's not lose sight of that past 20 years of experience that we have on the International Space Station. We've been incorporating a lot of the lessons learned into several of the systems. There's plans right now for a lot of upgrades on the regenerative life support systems that we currently have. We're looking at upgrades to things like Sabatier, the oxygen generator, and water processor. As Robyn mentioned, we're also doing a lot of flight experiments, getting ready to launch that waste management system hopefully this month. We're running things like the thermal amine scrubber, on a long duration test, and then next year, like Robyn had typed out, we're bringing up that brine process. So a lot of good technologies being tested. We're really looking forward to getting some of these ready for the missions to the moon and then eventually to Mars. That's all I had. My last slide, Grant, back to you.
Thank you very much, Darren. Okay, we're going to get into the questions that I have for the panel. And Robyn, I'm going to hit you with the first two. The first one is going to be a little bit more geared towards the moon. The second one, then extensively the extension to go into Mars. So first question is, given the schedule for the Artemis, which is the Halo and the HLS program and Gateway vehicles, do we really have time to build and test the Eclipse before we need them for those programs?
Yeah, hey, Grant. Yeah, I would say we do have time. The early missions are not relying on the full regenerative Eclipse. So the initial boots on the moon and the lander that, that Chip is working on, is going to have a more limited, what we call open loop Eclipse. It's not till we get to the more sustained capability that we're going to need the more full regenerative Eclipse for these initial missions. So we have a little more runway. That being said, we still need to keep the pressure on for two reasons. One, we're using the space station as our primary test bed. And so we're not going to have the space station forever, as much as I would like to believe that we are. And we need to keep the pressure on ourselves to get all the time on the system that we need while we do have a space station. And it takes a lot of time, as the slides I was showing earlier have taught us. So we need to keep the pressure on to get these systems ready. But the initial missions, we've got a little more runway we don't need everything by then.
Okay, great, thank you. And then thinking on to Mars surface, sort of a related question, given the potential trip for Mars and say we've heard 2033 or so, what is the setback schedule for the surface Eclipse for Mars? When do we need to start on that so it's ready to go?
Yeah, good question. We're really more driven by a schedule for the transit part of that mission, because that's our initial mission to Mars surface, I think is going to be, more like 30 days. And so we're going to, again, have it more, we can use a more open loop capability while we're on the surface, at least for the initial surface mission. But that transit Eclipse is going to be that round trip in the vehicle is going to be the challenge for us. And that's where we're going to need more of the long duration regenerative system. So that schedule, sometime in the 2030s, we set back from there. We don't have just loads of time. We're going to have to decide in the next coming years what our initial concept is for that vehicle. And we're going to base that, again, on what we learned for our ISS testing, and start there while we're still collecting data on that system in LEO.
Well, great. Thank you very much. Okay, this next I'm going to ask of Darren and Ted and Chip, what ISS Eclipse technologies do you think are directly applicable to the transit to Mars and they need to be proven on Gateway or Halo? And let's ask Darren first, just to go there.
So if you ask me, I'll say we need all the regenerable life support systems. So the oxygen generator, water processor, CO2 removal, brine processor, waste management. I can't think of a system that we wouldn't want to eventually put up there. I think you got to focus on the ones like CO2 removal first. That's probably more important. And then, you got to figure out how do you get your water recovery. So, things like water processor and oxygen generator would come up quick. I also think we need to focus on things like, trash compaction and radiation protection. Are there ways to pull out water? Robyn talked about trying to pull the water out of the food waste. We should also be looking at, can we pull water out of things like feces? So there's a lot of technologies that I think, we really got to focus in on, over the next 10 years so that we're ready to take a trip to Mars by 2033.
Okay, Ted, do you have anything to add to that?
Yeah, I think there's a natural progression of building off what was an ISS and looking at how do we add to the automation and the maintenance capability and doing a test run on the Gateway system outside of low Earth orbit. We haven't, I think I counted it up, that we have around 2,000 hours of life support experience beyond LEO. And I think you'll get 10 times that with the first mission to Mars. So a lot of these pieces of equipment and technologies will be directly applicable, but maybe the implementations with the additional capabilities of diagnostics, maintenance, we need to be able to prove those out before we take that first trip to Mars. And I think that's a real benefit with the Gateway. Eventually, the same goes for the surface system because of the long durations on the moon.
Okay, and now Chip, I know you're working on the moon lander, but I'm going to let you have a chance to answer that question too. Chip, we can't hear you. Okay, we seem to be having an audio issue with Chip on that. And while the people in the back room are trying to fix that, let me go on to the next question. It's going to be for you, Darren. How does industry design an Eclipse system to allow for repair and upgrades in cislunar or Mars transit or other zero-G environments?
So, I sort of talked a little bit about this in my opening, but, hardware is really going to have to be designed for in-flight repair, right? So, things like common parts, standard interfaces, right? Stuff that we don't currently do today. Also need to think about, if I'm designing hardware, I have to design it so that it can be tested on orbit with limited test equipment, right? So there's going to be limited things that we can do. You have a lot of systems that are pressurized. You got to figure out, how do I depressurize it? And then when I put the new one in, how do I leak check it? Things like that. So there's a lot of things we need to consider as we design this hardware for the future. Also looking at things like additive manufacturing and potentially in-space manufacturing. A lot of times you can design hardware that's much more complex when using additive manufacturing, and if you have the ability to grow it on orbit, even better. The other advantage with additive manufacturing, it really reduces part count. So, on our aircraft side of our business, we've invested heavily in this, really trying to look at things like, if I take a part that used to have, 120 parts and I can get it down to 10, that's a big weight savings, and it really cuts back on the complexity. And finally, really in our systems, when we design them, really designing in that smart systems. We need hardware that's going to be able to self-predict if it has issues, and then either the system either repairs itself through operation, or will shut down and say, hey, you got to come back and modify the impeller. You got to change out a fan. Those are the kinds of things. And I think Ted talked a little bit about adding more sensors and stuff. And I agree. That's something that we really got to look at. You got to make sure you have all of those things incorporated into the system so that you can have them work autonomously.
Okay, thank you very much. And anybody else want to add to that? Either Ted or Chip or Robyn?
Yeah, Grant, do you have me back now?
I do.
I'm sorry, I can hear you now. Yes.
Okay, great. I just was going to circle back to the previous question, which was about testing hardware, I believe, and how that might be done in landers. So, really the initial challenge that we're looking at with landers is oxygen management, particularly to support EVA activities. We have a lot of, driving requirements for supporting EVAs. Of course, we go on the surface. We want to get out of the vehicle and do things. So, oxygen management's a big issue. We have to carry, at this point, we have to carry gas down to the surface and store it at high enough pressures that we can run the bliss on. So I think headed to the direction of a high pressure oxygen system is a real challenge, and something that we ought to go pursue for the for not only the lander program but the future lunar surface habitats.
Great. Hey, Robyn, I'm going to change up an order of a question just because I haven't heard from you for a little bit. So, and it actually has come up, I noticed, in a few questions from the audience. But for Robyn and Chip both, do we have a radiation solution at this point in time, and specifically maybe galactic radiation, the higher energy radiation?
I get this question almost every year. And sorry, my connection dropped for a second there. I didn't mean to leave you hanging. And yeah, I would say we don't have a good solution for GCR. We have, for solar particles, we can do a pretty good job with shielding and actually predicting when those events are occurring. We're working on our forecasting models to be able to do a good job predicting events so that we can alert the crew and have them get in their protected area. GCRs are trickier. We are working on some active shielding technology that looks kind of promising, but it's still a ways off. I think it probably is going to be more potential, at least more feasible for a surface application than an in-space application. But I'll let Chip respond to, maybe he has a trick up his sleeve.
Yeah, I wish we did, Robyn, but this is something we're, of course, working heavily on as well. And it's, it's fairly early in the HLS program. We kind of like our design. It has kind of an umbrella effect on the crew cabin. So we think we have some advantages in terms of mass and other hardware that's providing some shielding indirectly. But you know, I agree with Robyn. We've got some opportunities to go, you know, to help go work this problem. We're doing some collaboration right now with the NASA teams on, you know, really understanding for our design what the, you know, what the problem looks like, so we can go do some mitigation on it. And, you know, again, as we get more mass capability to get hardware staged at the gateway and down to the surface, we think we can, you know, solve this problem eventually in the future. So that's where we're headed.
Okay, this next question I'm going to direct to Ted first, and then Darren and anybody else can jump in. But NASA has asked for a sustainable moon operation. So Robyn had said, you know, 2024 is short term, but then we talk about sustainability by 2028 that I know the administrators talked about. So how is moon's sustainability and Mars surface sustainability the same, and how is it different? So Ted, I'm going to hit you with that one first.
Okay, thanks, Grant. Interesting. We think that the lunar surface sustainability will help get us to Mars. When we think about it, we're talking about repeatable landing access for people to the surface of the moon, ability to land large cargo, and enablers such as power, lots of power, and ISRU to deal with, you know, provide consumables, whether that be fuel or oxygen, water, or nitrogen. And a lot of those things are needed. We can start on the moon, and then eventually they'll all be needed on Mars. The difference with Mars is obviously the distance. You know, it's a much longer trip, as Robyn shown in her first messages, or one of her first slides. Mars does have an atmosphere, which could be reused for used for different things. And if you're going with ISRU, the fuel source for the rockets might be different. And the other difference is you'll have to deal with dust in both environments. But we kind of see that being able to crack the ISRU and the power on the moon will basically help us repeat the same put the same capability on Mars.
Okay, and Darren, you want to add anything to that?
Yeah, I mean, I agree with Ted. You know, the obvious thing is the transit time and then the communications delay, right? So on the moon, obviously, it's not as big of a communications delay, but there will be some. But you know, I think it's a good place to, you know, at least try to learn how do we deal with that. You know, they're similar in that they're both pretty remote, not a lot and lots of dust, right? So you look back at the Apollo days and the issues they had with dust, and I think, you know, that's going to be one of our biggest problems, is trying to deal with, you know, dust mitigation, and how do you keep it off of the equipment, and how do you keep it out of the habitats. So obviously going to the moon first, I think, will be a big plus for that. And then, you know, lastly, the ISRU, really trying to understand, you know, how do we take the resources and turn them into something valuable. You know, things like mining water from the regolith and stuff on the surface of the moon. You know, those can be directly applied when we do a mission to Mars, which will be much more important when we get to Mars. So it's kind of along the same lines. But I think, you know, doing that moon mission first and then going to Mars is a really important step in deep space exploration.
Okay, and then Chip, do you have anything to add?
Yeah, and I agree with Darren and Ted as well. But, you know, really you know, the biggest challenge, you know, a lot of these systems we're talking about for lunar surface ops that will, you know, be developed into sustainable systems are very similar, if not the same, for a Mars type exploration. I think the biggest issue, though, is our mass problem. When you start looking at the problem of gear ratios and what it takes to get mass on the surface of the moon versus into a Mars orbit, and the surface of Mars is you know, it's a huge exponential type problem with mass. So, you know, I think as we continue to build these capacities for commercial launchers and NASA operated launch systems, it'll I think that's the biggest key to kind of opening up the sustainability for a Mars type mission.
Great. Okay, and I'm going to throw in two things there. I know I'm the moderator, but the two things I didn't hear mentioned. One is a very different thing between Moon and Mars is the thermal environment and how the thermal side of environmental control is going to be handled. I can see that that's going to be something that we got to know how to handle on the Moon, but it's going to be very different. And then also because it's near and dear, and we're going to have probably an audience question about it, dust. The one thing I know that I've run into is that dust on the Moon will teach us a lot of things about handling dust. And I have some, let's just say, some reservations about being able to transfer that over to Mars dust, because Mars dust and the morphology of Mars dust and Moon's dust is so different. So let me go on here. In a little bit related to that, what are the different technologies that would be employed for the surface Eclipse versus a transit Eclipse? What are the functions and the technologies involved? And I'm going to hit Ted with that one first.
Okay. If we go through the shopping list of Eclipse functions, if I look under environmental monitoring, we have pressurization, temperature control, and humidity control. We'll need those up on both. If we look at atmospheric management, we've got oxygen production, CO2 removal, CO2 reduction, filtration, trace contamination, ventilation, and all those are on both systems. Some of the differences in atmospheric monitoring and atmospheric management might be, like you said, the dust, be less on the transit, more on the surface. And if we do get RSRU working, then obviously we could be taking in oxygen or water directly into the system from Mars, and so that would be a little different. Water management, wastewater recycling, wastewater for oxygen and storage, trace contaminants removal in the water, waste management, solid waste and liquid waste management for both. They'll probably be easier to deal with the waste and on the transit. We'll have to get good at recycling and disposal. Differences, like I said, I think the transit waste management will have an easier time. And I think there'll be some special considerations in and around driven by planetary protection on the surface systems. When I look at it, most of these things can be common. And if we go into the point where we can do a sparing, like Darren was saying, below the ORU level, most of this technology for the transit and the surface can be common. And by taking a transit flight, I'll gain insight into what might be how the system might operate on the surface. And I think that's important to look at, and it helps to address the sparing. And all this is with the goal of reducing the consumables. So.
Okay. This next question, I'm going to ask, it's going to hit Darren first, then Chip, and then Ted if he wants to. How long, and I know this is near and dear to a lot of people's hearts. I get the question a lot in my environmental control, why do we raise plants for oxygen and stuff? So how long will it take to work bioregenerative elements into the Mars surface Eclipse until it makes up an appreciable percentage of the functions? Can we do any of that on the Moon? Is it 5 years out, 10 years out, 20, 30 years out? Is it never going to happen? So Darren, I'll let you handle that hot potato.
Yeah, so I'll start by saying I'm not a bioregenerative expert, so I do think it's very important. I think we do need to develop these systems for long-term sustainability. My thought is you would start out at the subscale level, potentially use them as backups to existing mechanical systems, and then continue to grow that, over the years. I'd recommend obviously, working out these details on the Moon prior to going to Mars, or even in a gateway, in space. My thought is you could have these systems in place, probably in the next 5 to 10 years, if not sooner. I mean, it's pretty well understood. I'm not sure that they would be willing to use them as the primary, from the start. But I think it's something that we need to start looking at, as soon as we start our missions on the moon. So yeah, I think probably 5 to 10 years is a reasonable expectation for putting those types of systems out there.
Okay, Ted, do you have anything to add?
Yeah, I had a summer intern this year from University of Washington, and he as one of the senior projects did a bioregenerative system using algae. And his comment is algae can be tricky, hard to control, and difficult to predict. And he said the person running the lab was worried his algae would get loose in the lab. And so, but at the same time, he came back and said, there's certain places, and if you could actually have that, like the moon might be a perfect place if you could figure out an algae that was timed to day and night cycles for food production or energy production, and then, but and the final thought I have is, I think going to Mars, I think we're going to be real careful. I probably think there's life on Mars. And I think before we go into introducing more life, we really want to check that out. And so I'm saying 25 years.
Okay, and Chip, did you want to add anything on that? Especially the part about, is there anything regenerative we can do on the moon in maybe not the niche short, but the longer term?
Yeah, so I think the key is getting the capability on the surface, and in terms of a larger habitat, a larger facility that can be used to do some of this testing and demonstrating, like we've used ISS to do for the past 20 years. So, that's the key enabler, I think, to do this. And as far as when, I can tell you the lander systems we're developing today are capable of delivering payloads in this magnitude to the surface. Things in the range of a 10 plus metric ton type habitat. So I think the capabilities are being developed. Can we do it in the next 10 years? It's possible if that's the priority and that's the way we go. So, technology wise, I think it could be done in the next 10 years and have some things opened up to be able to do some of the research.
Great. And Robyn, I understand you're on there. This next question is for you. The ISS, as you've said in your introduction, the ISS has been a test bed. It's been the best test bed for long duration ECLSS. What are your thoughts regarding the ongoing transition of ISS and LEO stuff with respect to the test bed capability? How is that going to go forward? Robyn, can you hear us?
Hello, can you hear me?
Yes. Do you want me to repeat that question, Robyn?
I'm having such terrible time.
Would you like me to repeat that?
Everything keeps freezing.
Yeah, okay. Would you like me to repeat that question?
Yes, but it keeps breaking up.
Okay.
I don't know if I'm being heard.
I can hear you. Let me try. The ISS has been a test bed for long duration ECLSS. What are your thoughts regarding the ongoing transition of ISS and LEO with respect to the test bed capability?
Okay. Yeah, sorry, folks. My internet decided to flake out this afternoon, I guess. So it's the administration's policy that we not have a gap in LEO. And so that means that following the life of the ISS, that we intend to have commercial platforms take over in LEO, for which NASA and other government agencies will buy services from. So we've been trying to define our needs so that companies interested in developing those platforms know what kind of services we're going to be a customer for. And one of those needs is testbed services, and among those is ECLSS. So, so my vision is that we would continue to have an ECLSS testbed in LEO. Not only do we need to gather additional time on system as we're deploying these capabilities beyond LEO, but we need a testbed to be able to bring in new technologies and see how they work in microgravity. Experience has shown us that just ground testing alone doesn't give us that confidence that we're going to need to be able to rely on those systems for missions in microgravity in particular. So The devil's in the details a little bit. We can't simply pick up and move the space station Eclipse over to a commercial platform. I think commercial platforms are going to be designed with different interfaces. We're going to have to sort of re-engineer things. And so we've got some work to go to figure out exactly how we're going to do this. But so far, we've signaled to industry that this is one of our interests so that they can begin to plan for those capabilities, those test capabilities on those platforms.
Great, great. And I'm looking at the audience questions. I know we're going to have another question about commercial platforms that I'll hit you with later. So that concludes at least the prepared questions that I had. And so I'm going to go to some questions from the audience, and I've been looking and sifting them as we go along here. The first one is about spares and repair. It says, how should repair and spares rely? How much should we rely on repair and spares being bring along stuff that we thought ahead of time and put stuff in the spacecraft versus pre-positioning and maybe sending a precursor mission that plunks down this trunk of spares on Mars? So Robyn, I'm going to let you handle that one first.
Okay. Sending stuff ahead of time sounds like a great idea, and pre-positioning the spares. However, it's not going to help us for our ride out. So it will potentially help us once we get there if we've had a problem along the way and need a spare part we didn't plan for the return trip. However, to get it from the surface back up to the mothership, the MAV is only going to have a certain capability. So I think, again, the more robust solution is to plan to bring everything we think we need for the mission and not rely on that pre-positioning, which is our current strategy.
Okay. Does anybody else in the panel want to handle that or our answer? I'm getting a lot of no's, it looks like. So the next question then, this is more of a technology question, so directed towards Ted and Darren. I think somebody mentioned that they were surprised about the, Robyn, when you mentioned the particulate monitor, that it implied that we didn't have one prior or not a capable one. So what is the need for a particular monitor, and what will it do for us in relation to human physiology?
So yeah, we haven't had one on space station. Space station has particulate filtration, pretty robust particulate filtration system. And so we haven't really had the respiratory risk that I think we're going to encounter when we start doing missions where we're going to be bringing back into the spacecraft lunar and surface dust. And this, I'm trying to channel my particulate expert here, but those particles are smaller, they're more jagged, they're more harmful potentially to the crew, which is what kind of drove the need to begin to develop a capability for a particulate monitor so that we could alert the crew we have those respiratory hazards and protect them. So it's really driven by these upcoming surface missions. However, we want to fly it on station and begin to test it, and as well as gather data on what kinds of particulates we're seeing. And it helps us define our load model. What are the types and sizes of particles that we are seeing so that we can better design our filtration system as well.
Great. And now Darren or Ted, why don't we go to Darren first about particulates? What's your thoughts on them?
Yeah, I mean, I agree with Robyn. We haven't had that capability to date, so having this up on orbit, I think, is a good thing. Often worry about particulate from other things like fires and stuff too. So I think I'm not sure if this particular monitor is tied into the combustion air monitor that they're also getting ready to fly, but excited to see it going up. I think it's important, especially for a mission to something on the surface of the moon or eventually to Mars.
Grant, I think the the particulate monitor will become very important as we get towards dust mitigation techniques and whatever we're doing on the lunar surface. You know, if we're going to go put in filtration systems and dust capture systems, we want to know how well it's working. And by establishing a baseline of what we've seen on ISS, we can tell, you know, roughly the difference between them. And so having something, a particulate monitor that's space qualified, will help us, you know, assess how well the lander systems are working as far as mitigating the dust exposure on the crew.
Chip, anything from you? Oops, Chip, you're muted right now.
I think we lost his audio again.
Sorry about that, Chip. We'll maybe circle back to you on that. I do have a question here that's definitely down path of everybody here. Maintainability versus reusability. Where do you draw the line between maintainability, which is really being able to replace parts, versus reliability, having the redundancy so that you don't have to replace parts? When it comes to Eclipse components for a Mars mission, where do you draw the line between them? And Ted, go ahead.
I think you're going to have a certain level of redundancy that you're going to need to have a high success rate with the mission, so there'll be a certain base set of capabilities that are there that'll probably be redundant in some fashion. And if something does fail, then you'll take the opportunity to see if you can fix it or not. But the primary mission of going to Mars is not to fix the equipment, but to explore Mars. So, so there'll be a base level, and I would expect that there'll be opportunities to repair things, to put it back into service. But I think most of the energy will be on the Mars mission rather than, you know, upgrading or repairing the equipment.
Mm-hmm. Darren, do you want to try that one?
Yeah, I mean, I agree. You know, I think the focus really needs to be on reliability and redundancy, but, you know, you will have to design things to be maintained. You know, there will be things like filters that are going to have to be replaced. There's going to be, you know, things like on the International Space Station right now, you know, they have to vacuum out a lot of the fans, you know, on a monthly basis, if not more. So there is stuff floating around. You will have to take care of it. I think, you know, we've learned a lot so far on the International Space Station. I think, you know, those lessons learned will go forward on the Gateway and then eventually on a mission to Mars. So yeah, I'm not exactly sure where we draw that line, but I think in general you want to design things so that you never have to touch them again. But you know, we do know that there will be things that you have to fix and maintain as you go forward. And like I said, things like filters, you know, that's probably one of the biggest areas right now that they spend, you know, every week vacuuming out certain areas, and you could potentially design around some of that.
Okay, and then Chip, if we've got your audio fixed, do you have anything to add?
Okay, I hope you can hear me now.
Yes.
Great. Yeah, I was just going to circle back to the last question, and really Ted answered it. You know, our biggest concern is dust contamination in the landers, and really understanding how to address that both inside the module as well as around the spacecraft, you know, for a reusable spacecraft. And as far as internally, we are planning to fly some monitoring equipment, so you know, so we can learn about that. So that's the I guess the question on the particulate counting. As far as maintainability from the vehicle side, I really don't like either one of them, but in either case, you know, we have to design to maintain these systems, of course, and that's what we're going to do. So.
Mm-hmm. And Robyn, did you want to add anything?
Well, yeah, I agree with everything that's been said. The point about reusability, I think, when I think about that versus maintainability, I'm wondering, refurbishment and reflight. And so if we're going to fly a mission to Mars and come back and say dock to the gateway and then do another mission, where do we draw the line between just replacing everything and being able to reuse it? That's an interesting question. I think it gets down to economics. Some of our commercial partners are really pushing the envelope on how do we reuse systems that we never would have thought to reuse before, and how can we certify those for the next mission? So I think that's an interesting question, and there's probably a good trade to be done there in an affordability regime where you think about what you would try to refurbish and reuse versus just replace.
And I want to add in one thing here too. I know from Paragon's perspective, we think some things have to be redundant, but everything will have to be maintained. The redundancy really comes into how critical is it? How fast do things go south if it fails? So you need to be able to switch on to a redundant system if you have a failure to maintain the livable environment. But you're eventually going to have to maintain the thing that crapped out on you on that's the redundant item, because you don't want to be flying along, say you're halfway to Mars and you lose one redundancy and you never try to repair it before you come back. So we always have to keep that in mind. And so it's redundancy, and you need immediate redundancy for critical things, and then everything eventually has to be maintained. So you have to think about maintainability for pretty much everything. Next question I'm going to ask Robyn here, because it's come up a little bit in all of our talks, as a matter of fact, which was additive manufacturing. Have we really started to develop in it? And we've mentioned it a lot, but do we have a viable path to having this additive manufacturing on board and ready to go?
We're definitely working on it. We're working on it. Our industry partners are working on it. Darren mentioned it quite a bit, as well as the others on this panel. I do think it's a key capability. We can imagine how wonderful it would be just to be able to print anything we needed to as far as spare parts on board. That would just solve all kinds of problems for us. I think the trick is going to be, Darren touched on this, designing for that, right? And then the precision assembly that's going to be required. You could print a new bearing in a pump, but then how do you get the pump reassembled with all the tolerances that you're used to being able to do on the ground? How do you do that on orbit? I think the key will be to do some test cases like that, and we're starting to look at that with our partners who are developing these capabilities, and maybe helping them from an Eclipse perspective with some of our more challenging potential things that would break. Let's design for trying to design for an additive manufactured part, and then being able to replace that part on orbit would be a really interesting demonstration that I firmly believe we should do. Okay,
great. Did I hear somebody else want to handle that too, or answer it? Okay, so the next one here, also for Robyn. Will the planned commercial space station from Axiom allow you to do faster or better testing of these systems?
Yeah, we are planning for a commercial element on space station. We've enabled our forward Node 2 port to be able to add this commercial element, and selected Axiom to develop that commercial element. So we're looking forward to that capability being added to station. And then the idea would be that, yes, we would begin to use it for stuff, research, test bed services. That's kind of the whole point, is can Axiom demonstrate a capability that not only the government can use, but other commercial customers can use while attached to station, and they don't have to think about building an entire free-flying platform from the beginning. They can take advantage of the infrastructure we have there, and then break off at some point and become a free flyer. So we're highly supportive of that. and looking forward to eventually getting that capability on station. And yes, moving some of our testing into it if we can.
Okay, this next one just came in, and I'm going to ask Chip first, and then Darren on this. Is there any chance that the EVA suits will remain outside the habitat? And Chip, I wanted to ask you from your standpoint of the Mars, the moon lander, and then Darren, because of course Darren's company builds spacesuits. It's one of those that's built spacesuits.
Okay, is there a chance? I think the answer is yes. I think the suit development that's been done on the NASA side has had that kind of in mind to, help alleviate some of the issues with airlocks and, gas management that I mentioned earlier. So, there's concepts out there for the rear entry suit, which is bulkhead mounted with no airlock. So, I know that that's being studied heavily. I think the initial demonstrations will not have that capability. Get some confidence in the landing systems and the airlocks and the suits themselves. So, is it possible? Yeah, I believe so.
Okay, and Darren, how about you from the standpoint of a company that builds spacesuits?
Yeah, I mean, I think that's a concept we've been looking at for several years. I know we've done mock-ups and testing of that over the years. I think that's kind of the going forward plan. When you look at stuff like the XEMU, it looks like it's going to be a rear entry suit. So I think that kind of is the vision going forward. So you would like to leave that suit outside, on the surface of the moon, so you're not bringing all of that dust back in every time you go out for an EVA.
Mm-hmm. And Robyn, I know that's not necessarily your area, but do you have any comments on that? Not to put you on the spot. Oh, we may have lost her there. Okay, I have another question here. I'm going to ask for Ted first, and then Darren is, have we looked into designing the Eclipse in a way to make them more robotic friendly? Perhaps each box would consist of multiple sub-functional units capable of being replaced by a robot and stuff. So have we thought about robotic maintenance, since we've been talking about maintenance a lot?
Yeah, we're starting to look at that. I think that makes a lot of sense when we start looking at repairing things below the ORU and looking at replacing common components across multiple types of subsystems. Darren went into some pretty specific detail on his next step work, and I think that's a critical enabler to allowing robotic maintenance of that equipment. I think that'll be crucial for things that are that need to be operating before you get there, to have a robotic maintenance capability. But I'll let Darren talk about next step.
Yeah, so we did a fair amount of work with the robotics team at JSC, having discussions on trying to incorporate those features into our designs. I think for things like the gateway, where it'll be dormant for months at a time, having that capability would be a big positive. So yeah, it's something we're certainly looking at, something we're certainly interested in. I think there's a lot of work that still needs to be done, but I think that will be the future. Within the next 10 years, I think that's something we certainly have to have going forward, especially when we have things like the gateway that may be sitting dormant for several months at a time. To have that robotic ability to fix things or repair things will really help us.
Great, yeah, and I will relate. Back when I was on the space station program in 1987, I remember one of the requirements from NASA is thou shalt make the space station solar arrays, in that case, robotic, able to be maintained robotically by the SPDM. And my first question is, do we have a specification for the SPDM? And they said no. So it was really hard to design that, I can tell you that. This is going to be the last question. We're getting down on time, and I'm going to direct it towards Robyn first. But others can maybe call in. But we've mentioned a lot about lessons learned with ISS. And is there a vehicle or a method of disseminating lessons learned about ISS? And before you answer, I'm going to say you better mention the International Conference of Environmental Systems in your answer.
That was going to be top of my list. Yeah, unfortunately, we didn't have to have the in-person conference this year. There were papers out there though, and yeah, lessons learned on ISS. We sure have learned a lot of them, and we do try to write papers about it and give talks and conferences whenever possible. We also have try to put some material out on NASA sites. We have some lessons learned capturing sites out there, as well as just kind of pass them down amongst us getting to be graybeards to our newer employees along the way. And it's always tricky. It's tricky to get word out and compete with everything out there. I would say the resources are there. We probably don't always do the best job of disseminating the resources. We do what we can with conferences and things. So if anyone has some great ideas for us and ways we can do that better, I'm happy to hear them.
Right. Okay. Any other comments before we close up here? We've got about 1.5 minutes left, and just anything that was questions or go backs that any of the panelists have. Boy,
so
go ahead, Ted.
The only thing I would add about the ISS lessons learned is when we go talk to grade school students and such, being able to relay something that was actually on space or show them that was an ISS gets that excitement up. And what I found is someone who has a passion will go out and find things. And if you just point them in the right direction with, go talk to this person, technology and knowledge transfers through people, and pointing them in the right direction with the right, the right person they'll find the answer. Yeah.
Mm-hmm.
I will put in a plug for ISS 20. I'm wearing my shirt. We got a lot of great resources out. If you look at the website, lots of fun facts and figures, but also some really great results and benefits that have come from the ISS. So I would invite anyone online to visit that site.
Okay, well, with that, we're down to our last few seconds. I want to use those seconds to thank the panel from the bottom of my heart. I know that this is a difficult time for everybody, and everybody knows we're really busy, but to take this time for this panel really shows that we want to get out and let the world know what we're doing, because, man, we're going to the moon, we're going to Mars. There's a lot of excitement going on in our industry, and I hope we've conveyed a little bit of that too. Thank you very much for your time, and I'm going to hand it back to the Humans to Mars Summit. Thank you very much,
Grant.
everybody.
Thanks, Grant.
Thanks, Grant.